So that's one cosmological test. We can measure the density, and it seems to be suggesting there is not enough matter in the universe to be critical flat. It actually must be open. But there's another possibility. Remember we talked about, depending on the density of the universe, you get different geometries. The universe could be a spherical geometry, something like this, in which case pi is less than 3.141592, and eventually if you go far enough you go all the way back.
So I've always wanted to do an experiment, Paul, which is where we're here at Earth, and we get a graduate student. We actually get 2 graduate students, and you send one off that direction as fast as you can. We'll say 99.99% of the speed of light for 1 billion years, and another one that direction, same deal. And then after 1 billion years, we all get together, and we measure the angles between us, and that, they add up to more than 180 degrees. We know we're in that universe.
Well, that's the problem. It would be nice to measure the geometry by trying to see if the angles don't add up, or if pi is not right, or something like that. But if the universe is curved, it's curved on scales of billions of light years, so we'd need to have a billion-year experiment at the speed of light to do anything. But is there some way we can actually try and measure the geometry of the universe just stuck here on Earth by just looking?
Well, one thing to think about is if I go through and I measure the volume, or the surface, the area in this case, but the volume of a spherical universe, it's going to be less as I go to larger and larger radii than in the flat case, right? Because my value of pi is changing. And so that's a way we might be able to think about looking and seeing how much stuff there is out at different distances.
So if we could find something that was spread uniformly through space,
Galaxies.
and count the number within a volume,
Yep.
and as the volume gets bigger and bigger, if it's a flat universe, the number per unit volume should remain the same. But if it's a universe that's got a spherical geometry like this, as we make our spheres bigger and bigger and bigger, then we're going to get increase less. Eventually, if you made it all the way around to the far end of the universe, you might not be seeing any more galaxies at all.
Great idea.
Likewise, if it was a saddle-shaped universe, an open universe, which is what we're thinking from the dark matter, in that case, there's more volume than you expect from 4/3 pi r cubed out to large distances. So as you go fainter, the number of galaxies should increase faster.
Okay. So let's think about the number of objects we're going to see
Per unit volumes.
per unit volume. And so
The trouble with that is we can't easily measure distances to these
Yeah.
things. We're going to come back to that big time a bit later on in this lesson. But if you remember in the first course when we were talking about gamma ray bursts, we came up with an interesting way around this problem. If you have a population of things that are all the same, scattered through space, the ones that are near, they all have the same luminosity. The ones that are near are going to appear bright to us, and the ones that are going to be further away are going to appear fainter. But there's more volume if you go further out, so as you look fainter you should see more and more of the things because you're reaching a bigger volume of the universe.
Right.
And we did the calculation back then and showed that the number we see should be proportional to the flux to the -3/2 power.
And that's because the volume goes, the number goes as the cube of the distance, but the flux or the brightness goes down as the square. So you get the volume with the cubed, the distance, and the square is the diminution of the flux. So that's how that comes out.
Okay, so this is a possible test. We should count the number of, find something that's spread through the universe, quasars, radio sources, galaxies, gamma ray bursts, whatever, and count how many bright ones there are and how many ones there are a bit fainter and a bit fainter and a bit fainter. And the number count should go like this if it's a flat universe. If it's a closed universe, the numbers will increase less. If it's an open universe, they'll increase more.
Good.
But there is a complication. In calculating this, we assumed the inverse square law. So the idea was that if something is given luminosity, the flux we see is equal to the luminosity divided by the area of the sphere that includes us, because the photons have had to spread over a bigger and bigger sphere. But that's also going to be affected by curved space. So imagine if you're on something like this and you've got a light source over here that's shining out, the photons have to spread out over a sphere whose surface area is less than 4 pi r squared. So that's going to make them appear brighter than they'd otherwise expect.
Right, and if you're in the saddle universe, it's the opposite. It ends up being spread out over a larger space. So that means the distance we infer from how bright something is going to be a little different. It's actually going to depend on the shape of the universe.
Yes, and in fact we can calculate this for different models, and the way we do it is we come up with something called the luminosity distance, which is not the same as the distance you get with a tape measure. It factors in this size of the sphere. It also factors in the fact that the photons get stretched by the expansion of space,
Okay, yes.
and the fact that the arrival times of the photons get stretched. If you have a whole bunch of photons arriving, maybe one a second, because of expansion of space it might be one every 2 seconds.
Okay,
So you have to factor all those things in. It's complicated, but for any given cosmological model you can work out what this is, and we'll put a link into the course to a calculator so you can see it for yourself.
Yep.
And so you can then use this modified version of the inverse square law. So it all becomes a bit mathematically complicated, but for any model you can predict what you see. And what do we see? Well, we see too many things.
Right, the universe is just full of stuff.
And there are too many faint things compared to bright things.
So doesn't that just mean the universe is open?
Well, it could, and that was what people often thought when they first encountered this. But it's a bit confusing because we have to be looking at distances of billions of light years. And that means we're looking back 20, 30% of the age of the universe. And it could be that galaxies are just different back then than they are now. In fact, almost certainly they are.
Yeah, because these galaxies are very, very small, and it turns out they're much smaller because if we calculate how big they are, they'd be much, much smaller, the average galaxy here, than what we would see in the Milky Way, for example. So these galaxies just don't really look like the galaxies that we see around the Milky Way today on average.
I mean, you'd think you can count the number of galaxies per unit volume, but for a start, galaxies might collide with each other, so the numbers could be going down because of galaxy collisions.
Yep.
But more importantly than that, we're not actually measuring, no telescope can measure the number of galaxies in a given volume. All you can measure is the number of galaxies above some brightness threshold in a particular volume. And so you can say down to the limit of a particular telescope we can see so many galaxies in a unit volume. But it could be in the early universe galaxies are brighter than they are now because they just formed lots of stars, and if the stars have only just formed, the very massive hot stars are still going to be around, and they put out tons of light per unit mass.
We certainly know they're changing over time because if we look back 13.8 billion years ago, we know there were no galaxies at all. So something's changing over time. So galaxies are changing over time. So that's going to really mess this measurement up, isn't it?
So in principle, this is a really nice way of measuring geometry, but in practice, you have to fully understand how galaxies evolve with time to use it, because you have to subtract that off to find out what's really going on with geometry. And we don't understand the evolution of galaxies in anything like enough detail.
Well, that's actually one of the big questions of astronomy is how do galaxies evolve? So it seems like a bit of a problem here for us.
So it sounds like measuring geometry, nice in principle, won't work in practice.